In 1929, Edwin Hubble sat in an office at the Mount Wilson Observatory above Pasadena, working through a table of numbers he had been building for years. The numbers were distances to galaxies, which was already a strange thing to have, because only a few years earlier, nobody was sure galaxies existed at all. What Hubble had noticed, and what he was trying to make clean enough to publish, was a pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. Not randomly faster. Proportionally faster. Double the distance, double the recession speed. Triple the distance, triple the speed. It was a straight line on a graph, and straight lines in physics tend to mean something deep is going on. Hubble was careful about it. He published the data, drew the line, and mostly let other people argue about what it meant. But what it meant, once you followed the thread far enough, was that the universe is expanding. Space itself is getting larger. And that single observation, that simple straight line on a piece of graph paper, opened a question that sounds like it should have a straightforward answer, but absolutely does not. How big is the universe really? Not the part we can see, not the part our instruments can reach, the whole thing. The real size of the universe turns out to be stranger than infinite, in a way that takes some unpacking, and that is what tonight is about. So settle in. Let your breathing slow down. We are going to take this gently, one piece at a time, and if you drift off somewhere along the way, that is perfectly fine. Let's start with what Hubble actually measured, because the method matters as much as the result. He needed two things for each galaxy: how far away it is and how fast it is receding. The speed part was, relatively speaking, the easier half. It came from something called redshift, and it works like this. When a galaxy is moving away from you, the light it sends in your direction gets stretched. The wavelength gets longer. Longer wavelength light is redder, so the whole spectrum of the galaxy shifts toward the red end. You can measure that shift very precisely by looking at the specific wavelengths that hydrogen and other elements absorb. Those absorption lines act like a fingerprint. You know exactly where they should appear, and you can see exactly how far they have been nudged. The size of the nudge tells you the speed. Vesto Slipher, working at the Lowell Observatory in Arizona, had already measured redshifts for dozens of galaxies by the time Hubble got involved, so the speeds were available. The distances were the hard part. They are always the hard part in astronomy. You cannot stretch a tape measure to another galaxy. You cannot bounce a signal off it and time the echo. What Hubble used was a type of star called a Cepheid variable. These are stars that pulse, brightening and dimming in a regular cycle, and a woman named Henrietta Leavitt had discovered something remarkable about them back in 1912. She was working at the Harvard College Observatory, one of a group of women hired to catalog photographic plates, and she noticed that the brighter a Cepheid was in absolute terms, the longer its pulsation period. A Cepheid that took 30 days to complete one cycle was genuinely, intrinsically brighter than one that took 3 days. This meant that if you could find a Cepheid in a distant galaxy and measure how long its cycle took, you would know how bright it truly was. Then you could compare that true brightness to how bright it appeared in your telescope, and the difference would tell you how far away it was, because light dims with distance in a predictable way. It falls off with the square of the distance. A star twice as far away appears 4 times dimmer. A star 10 times as far away appears 100 times dimmer. Think about what that means. Leavitt had handed astronomers a cosmic yardstick. Not a perfect one, and we will come back to the imperfections, but a usable one. Hubble took that yardstick, identified Cepheids in galaxy after galaxy using the 100-inch telescope on Mount Wilson, which was the largest in the world at the time, and paired each distance with Slipher's redshift measurements, and the pattern emerged. Farther galaxies, faster recession. A straight line. Now, here is the thing about that straight line. It does not mean what it seems to mean at first glance. The natural picture that forms in your head is of galaxies flying apart through space, like shrapnel from an explosion, with us sitting somewhere near the center watching everything rush away. But that is not what is happening. What Hubble's data actually showed, once the theoretical framework caught up, is that space itself is expanding. The galaxies are not moving through space away from us. The space between them is growing. This is a genuinely different thing, and it matters enormously for the question of how big the universe is. Here is an analogy that helps, even though every analogy for this breaks down eventually. Imagine the surface of a balloon being inflated. Take a marker and draw a few dots on the balloon. As you blow air in, every dot moves away from every other dot. No dot is at the center of the expansion, because the expansion is happening everywhere on the surface at once. A dot near the top sees dots near the bottom receding quickly, and dots nearby receding slowly, exactly the pattern Hubble found. The surface of the balloon is two-dimensional, and the expansion is happening in a third dimension that the dots have no access to. Our universe may be doing something analogous in higher dimensions, or it may not, but the key point is that the expansion is a property of space itself, not a movement of objects through a fixed space. This distinction between things moving through space and space itself expanding is the reason the real size of the universe is so much stranger than you would expect. Because if space is expanding, then light that left a distant galaxy a long time ago has been traveling through space that was stretching the entire time. The galaxy that emitted that light has been carried further away during the journey. By the time the light reaches your telescope, the galaxy is not where it was when the light left, and it is not at the distance the light's travel time would naively suggest. It is much, much farther away. Let's put some numbers on this, because the numbers are where the strangeness really lives. The universe is about 13.8 billion years old. Light travels at a fixed speed, roughly 300,000 kilometers per second, and nothing with mass can exceed that speed. So you might reasonably expect that the farthest thing we could possibly see is 13.8 billion light-years away. Light that has been traveling since the very beginning, arriving just now. Makes sense, right? But the observable universe, the sphere of everything whose light has had time to reach us, has a radius of about 46.5 billion light-years. Not 13.8, 46.5. More than 3 times larger than the age of the universe multiplied by the speed of light would suggest. And that is not a mistake. That is the expansion doing exactly what we just described. Light left a region of space 13.8 billion years ago, and while that light was in transit, the space it had already crossed kept stretching. The region it left kept getting carried away. By the time the light arrives here, the source is 46.5 billion light-years away, even though the light itself never exceeded its speed limit. The light obeyed every rule. Space just changed the size of the playing field while the game was in progress. So the observable universe is a sphere roughly 93 billion light-years across. That is already a number that resists being held in your head. Let me try to give it some weight. If you could somehow freeze the expansion right now and fly across the observable universe at the speed of light, The trip would take 93 billion years. The universe is not even 14 billion years old yet. The thing you are trying to cross is nearly 7 times older than the time that has existed. And that is only the observable part. That is only the light that has had time to reach us. Here is where the question deepens. The observable universe has an edge, but it is not an edge of the universe. It is an edge of our knowledge. It is the horizon beyond which light has not had time to arrive. There is no reason to think the universe stops there. In fact, there is very good reason to think it does not. The cosmic microwave background, that faint glow of radiation left over from when the universe was about 380,000 years old, is remarkably uniform in every direction. The patterns in it, the tiny temperature fluctuations that tell us about the density of matter in the early universe, are consistent with a space that is either flat or so close to flat that we cannot measure the curvature. And a flat universe, in the simplest models, is infinite. It goes on forever. Not eventually curves back on itself, not wraps around, just continues, with more galaxies and more space and more of everything, past every horizon you could ever reach. But here is the part that is genuinely hard to hold in your head. Even if the universe is infinite, that is not the strange part. The strange part is what the expansion does to an infinite universe and what it means for the regions we will never, ever be able to contact, because the expansion is accelerating. We found that out in 1998, and it came as a serious shock. And it changed the entire picture of what the future of the universe looks like and what the real size of it means for anyone trying to understand their place in it. The story of how we discovered that acceleration involves a particular kind of exploding star, a pair of competing research teams, and a result that nobody on either team wanted to believe. The teams were looking for a way to measure distances to galaxies far more distant than anything Hubble's Cepheids could reach. Cepheids are bright, but they are individual stars, and past a certain distance you simply cannot pick them out anymore. You need something brighter, something so luminous it can be seen across billions of light years. And the object they settled on was a Type 1a supernova, a very specific kind of stellar explosion that happens in a binary star system, and the reason it works as a distance marker is beautifully simple. A white dwarf, one of those dense stellar remnants about the size of Earth, but with the mass of the Sun, is sitting in a close orbit with a companion star. And it is pulling matter off that companion, hydrogen gas streaming across the gap between them, piling up on the surface of the white dwarf. The white dwarf gets heavier and heavier, and there is a limit, a very specific mass threshold called the Chandrasekhar limit, about 1.4 times the mass of the Sun, named after Subrahmanyan Chandrasekhar, who worked it out in the 1930s while he was still in his 20s. When the white dwarf crosses that threshold, something fundamental changes. The pressure inside can no longer hold the star up. Carbon and oxygen in the core ignite in a runaway thermonuclear explosion, and the entire white dwarf detonates. Not a collapse, not a partial eruption. The whole thing goes in a matter of seconds, releasing as much energy as the Sun will produce in its entire 10 billion year lifetime. Now here is why that matters for measuring distances. Because the trigger is always the same threshold, always 1.4 solar masses, the explosion is remarkably consistent. Not perfectly identical every time, there are variations, but those variations correlate with something observable, which is how quickly the light from the explosion fades. A brighter Type 1. A supernova fades more slowly. A dimmer one fades faster. And that relationship, worked out carefully through the 1990s, means you can watch a Type 1a supernova in a distant galaxy, measure how its brightness changes over the weeks after the explosion, and from that light curve figure out its true, intrinsic luminosity. Once you know how bright it actually was, you compare that to how bright it appears from here, and the difference tells you how far away it is. Same principle as Leavitt's Cepheids, same principle as any standard candle. You need something whose true brightness you can determine independently, and then the apparent brightness gives you the distance. So by the mid-1990s, two teams were racing to use Type 1a supernovae to answer a specific question. Not whether the universe was expanding, that had been settled for decades. The question was whether the expansion was slowing down, and if so, by how much. Think about what you would expect. The universe is full of matter, galaxies and gas and dark matter, all of it exerting gravitational pull. After the initial push of the Big Bang, you would expect all that gravity to be gradually pulling everything back, decelerating the expansion the way a ball thrown upwards slows down as Earth's gravity works on it. The big question was whether there was enough matter to eventually stop the expansion and reverse it, pulling everything back into a big crunch, or whether the expansion would slow down, but never quite stop, coasting outward forever at a decreasing rate. Either way, the expansion should be decelerating. That was the assumption. That was what everyone expected to measure. The only question was how fast the deceleration was. The two teams were the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory in Australia, with Adam Rees doing much of the critical data analysis. They were competitors, working independently, sometimes using the same telescopes on different nights, hunting for Type 1a supernova in distant galaxies, and then following up with careful measurements of the light curves and the redshifts. And the way you do this is painstaking. You image a patch of sky, wait a few weeks, image it again, and then compare the two images looking for a new dot of light that was not there before. A supernova going off in a galaxy billions of light years away. When you find one, you have to move fast because the light curve is changing night by night, and you need spectroscopy to confirm it is actually a Type 1a and not some other kind of explosion, and you need photometry over several weeks to pin down the peak brightness and the fade rate. Both teams were doing this work through the mid to late 90s, and as the data accumulated, something uncomfortable started to show up. The distant supernovae, the ones billions of light years away, whose light had been traveling for a large fraction of the age of the universe, were dimmer than they should have been. Not by a huge amount, but consistently, systematically dimmer. And in the standard candle framework, dimmer means farther away. The supernova were farther away than the decelerating models predicted. Think about what that means. If the expansion had been slowing down over time, then in the past, the universe was expanding faster than it is now, which means a galaxy at a given redshift should be at a certain distance. But if the supernovae are farther than that, it means the expansion was not slowing down. It was speeding up. The galaxies had been carried farther apart than a decelerating universe would allow, because somewhere along the way, the expansion started accelerating. Both teams checked and rechecked. They looked for errors. Maybe dust between us and the distant supernovae was absorbing some of the light, making them appear dimmer without actually being farther away. That was a real concern, and they spent months working through it. Dust does absorb light, but it also reddens it, shifting the color in a predictable way, and the color data did not support enough dust to explain the dimming. Maybe the distant supernovae were intrinsically different from nearby ones, because they formed in younger galaxies with different chemical compositions, That was harder to rule out, and it took careful comparison of the spectral features. But the signal held. In both datasets, independently, the conclusion was the same. The expansion of the universe is accelerating. Perlmutter's team published in 1999. Schmidt and Rees's team published in 1998. And neither team was happy about it. Rees has talked about this openly. He described going through the analysis and getting the result and then spending weeks trying to find the mistake because the result did not make physical sense. Gravity pulls things together. Gravity decelerates expansion. For the expansion to be accelerating, something has to be pushing space apart, something that acts like a repulsive force on cosmic scales, and there was nothing in the standard model of cosmology that did that. Or rather, there was one thing, but it had been abandoned decades earlier. Einstein had introduced a term into his equations of general relativity called the cosmological constant, originally to keep the universe static, before Hubble showed it was expanding. Einstein reportedly called it his biggest blunder and dropped it. And now, 70 years later, the supernova data was saying something very much like that constant was real. Some kind of energy inherent in empty space itself, pushing the expansion to accelerate. We call it dark energy now, which is an honest name in the sense that it tells you almost nothing. It is dark because we cannot see it. It is energy because it has to be something, some property of space, or some field pervading the universe that drives the acceleration, and it dominates the energy budget of the cosmos. When you add up everything, all the ordinary matter, all the dark matter, and all the dark energy accounts for roughly 68% of the total. The stuff you and I are made of, atoms, protons, neutrons, electrons, all of it, is about 5%. Dark matter is about 27%. The universe is mostly made of something we have never directly detected and do not understand. But here is where this connects back to the size question, which is really what we are circling. The acceleration changes everything about what the universe looks like in the long run, and it changes everything about what we mean when we say the universe might be infinite. Because in a decelerating universe, even if it is expanding, distant galaxies are getting farther away, but the rate is dropping, which means light from those galaxies has a chance, given enough time, to bridge the gap. The expansion slows, the photons keep coming, and in principle, you could eventually see farther and farther. But in an accelerating universe, the opposite happens. The expansion speeds up, and at a certain distance, the space between us and a distant galaxy is stretching faster than light can cross it. Not because anything is moving faster than light through space, nothing is, but because space itself is growing, and the rate of growth across a large enough distance exceeds the speed of light. And that means there are galaxies we can see right now, their ancient light already recorded in our telescopes, that we will never be able to contact. The light we are receiving from them left billions of years ago, when the expansion was slower, when the gap was crossable. But the light those galaxies are emitting right now will never reach us. The distance is growing too fast. This is what makes the real size of the universe worse than just being big. It is not that the universe is large and we are small. It is that the universe is actively getting less reachable. The observable universe, the sphere of everything whose light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. That is already strange, because the universe is only 13.8 billion years old, and you might think nothing could be farther than 13.8 billion light-years away. But expansion has been stretching space the whole time the light was traveling, so the objects that emitted the oldest light we see have been carried much farther away by now. That 46.5 billion light-year radius is the current distance to those objects, not the distance the light actually crossed. And the observable universe is not the whole universe. It is just our window. Beyond it, there is more, almost certainly a great deal more, and we have no way to know how much. The curvature measurements from the cosmic microwave background tell us the universe is flat to within about 0.5%, and a flat universe in the standard cosmological model extends without boundary. But here is the subtle thing that often gets lost. Even if the universe is finite, it could still be so large that the observable part is a vanishingly small fraction of the whole. And the accelerating expansion means that fraction is effectively shrinking. Not because our observable universe is getting smaller, it is actually growing as more ancient light reaches us, but because the total universe, if it is finite, is growing faster. And if it is infinite, then our observable patch was always infinitesimal compared to the whole, and the acceleration just makes the inaccessible part grow faster still. So you have this layered situation. The observable universe is enormous, 93 billion light-years across, but it sits inside a larger universe whose true extent we cannot measure, and the boundary between what we can see and what we cannot is not a wall or an edge, it is a horizon created by the finite speed of light and the age of the cosmos. And beyond that horizon, the accelerating expansion is carrying regions away from us so quickly that no signal, no probe, no message traveling at the speed of light, or anything less, will ever cross the gap. Those regions are not just far away. They are, in a very real physical sense, permanently out of reach. And this raises a question that cosmologists have been grappling with for the last 2 decades, a question about what it even means to say something exists if no observation, even in principle, even given infinite time, could ever confirm it. The answer depends on what you think the purpose of physics is, and it turns out that people have very different answers to that question. And those answers shape the kind of science they are willing to do. There is a tradition in physics, a long and productive one, that says the job of the discipline is to describe what can be observed. Full stop. If something cannot, even in principle, be detected, measured, or tested, then it is not a question for physics. It might be a question for philosophy, or for theology, or for late-night conversation, but it does not belong in a scientific paper. This is not a fringe view. It traces back through the logical positivists of the early 20th century, through Ernst Mach, who famously refused to believe in atoms because nobody had directly seen one yet, and it has a certain elegant discipline to it. You draw a line around the things you can check, and you work inside that line. And if you apply that thinking to the universe beyond our cosmic horizon, you arrive at a clean conclusion. Those regions, the ones the accelerating expansion has carried permanently beyond any possible observation, are not part of physics. They might be real, they might not be. The question is unanswerable, and unanswerable questions are, by this standard, not scientific questions. You shrug, you note the boundary, and you get back to work on the 93 billion light-year patch you can actually study. But here is the thing. There is another tradition, equally long and arguably more productive, that says the purpose of physics is to build the best possible model of reality, and if that model predicts things beyond the horizon, those predictions are part of the model and deserve to be taken seriously. Think about it this way. General relativity does not stop at the edge of the observable universe. The equations do not have a clause that says, "and beyond this radius, stop caring." The same physics that describes the expansion we can measure predicts that expansion continues in regions we cannot measure. And if you trust the model inside the horizon, where it has been tested to extraordinary precision, it seems strange to suddenly distrust it outside the horizon, where the physics is, as far as we can tell, exactly the same. This is not a hypothetical debate. It matters right now, practically, because some of the biggest questions in modern cosmology depend on which side you take. Consider the multiverse, not the comic book version, but the version that falls out of inflationary cosmology. Inflation is the idea, first proposed by Alan Guth in 1980 and refined by André Lend, Paul Steinhardt, and Andreas Albrecht in the years that followed, that in the first unimaginably tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Not the gentle Hubble expansion we see today, but a burst so violent that a region smaller than a proton could have blown up to something larger than the entire observable universe in less than a trillionth of a trillionth of a trillionth of a second. And inflation was not invented to be dramatic. It was invented to solve specific, nagging problems with the standard Big Bang model, problems that had been bothering cosmologists since the late 1970s. The biggest of these was the horizon problem, which is worth understanding because it connects directly to everything we have been talking about. When you look at the cosmic microwave background, that ancient light from when the universe was about 380,000 years old, you find that it is almost perfectly uniform in temperature. Pick a direction, measure the temperature. Now turn 180 degrees and measure again. The two readings agree to about 1 part in 100,000. And that seems fine until you think about it carefully, because those two patches of sky are on opposite sides of the observable universe. The light from one is arriving from roughly 46 billion light-years in one direction, and the light from the other is arriving from roughly 46 billion light-years in the opposite direction. Those two regions are separated by 93 billion light-years, and at the time the light was emitted, when the universe was only 380,000 years old, there had not been enough time for a signal traveling at the speed of light to cross from one to the other. They had never been in contact. They had no way to exchange energy, no way to reach the same temperature, no way to coordinate. And yet they are at the same temperature, to extraordinary precision. That is like walking into two rooms on opposite sides of a building that has no hallways connecting them and finding the thermostats set to exactly the same number. You would assume someone had set them both before the walls went up. And that is essentially what inflation proposes. Before the exponential expansion, those two regions were close together, close enough to reach thermal equilibrium, close enough to share energy and settle to the same temperature. Then inflation stretched them apart so violently that by the time the cosmic microwave background was emitted, they were far beyond each other's horizons. The uniformity was baked in before the separation, not after. And inflation works. It solves the horizon problem. It solves the flatness problem, which is the question of why the geometry of the universe is so close to perfectly flat, because inflation drives any initial curvature toward flatness, the way blowing up a balloon makes a small patch of its surface look increasingly flat. It even predicts the specific pattern of tiny temperature fluctuations in the cosmic microwave background, the seeds that would later grow into galaxies and galaxy clusters. And those predictions match the observations from satellites like COBE and WMAP and Planck with remarkable precision. So inflation is not speculation. It is a well-tested framework that explains things the standard Big Bang cannot. But here is where it gets strange, and where the question about what exists beyond the horizon becomes unavoidable. In many versions of inflation, the exponential expansion does not stop everywhere at once. It stops in patches. Our observable universe is one such patch, a region where inflation ended, where the energy driving the expansion converted into matter and radiation, where the familiar Big Bang evolution took over. But in the spaces between these patches, inflation may still be going on. And because exponential growth is so ferociously fast, the inflating regions grow much faster than the patches where inflation has ended. New patches keep forming, each one a separate post-inflationary region with its own Big Bang, its own cooling, its own possible structures. This is eternal inflation, and it was not designed as a wild idea. It falls naturally out of the mathematics of the inflationary models that best fit the data. André Linde was one of the first to recognize this in the 1980s, and it troubled him even as he developed it, because the implication is that our observable universe is not just one patch of a larger finite cosmos. It is one bubble in an endlessly self-reproducing foam of universes, and the total structure may be genuinely, irreducibly infinite. Now you might be thinking, this sounds like exactly the kind of thing that first tradition would throw out. You cannot observe these other bubbles. No signal from them will ever reach us. They are beyond the cosmic horizon by construction, separated from us by regions of still inflating space that are expanding far faster than light. So, are they real? And this is where the debate gets genuinely interesting, because the answer is not just philosophical. It has practical consequences for how you do science. If eternal inflation is correct, then the constants of physics, things like the strength of gravity, the mass of the electron, the energy of the vacuum, might vary from bubble to bubble. In our bubble, they have the values we measure. In another, they could be different. And if that is the case, then asking why our constants have the values they do might not have a deep, derivable answer. It might be like asking why you live on this particular street. There is a story behind it, but it is not a law of nature. It is a historical accident combined with the fact that you have to live somewhere. This line of reasoning leads to what is sometimes called the anthropic landscape, and it is genuinely controversial. Some physicists, Steven Weinberg among them, have argued that the anthropic approach actually made a successful prediction. In 1987, before the accelerating expansion was discovered, Weinberg used anthropic reasoning to estimate the value of the cosmological constant, the energy density of empty space. He argued that if the cosmological constant were much larger than a certain value, galaxies could never have formed, and nobody would be around to measure it. His estimate was rough, but it landed in the right ballpark, and when the supernova teams measured the actual value 11 years later, it was within the range Weinberg had sketched out. That does not prove the multiverse is real. But it is an interesting data point, and it is the kind of thing that makes it hard to simply dismiss the question. On the other side, people like Paul Steinhardt, who helped develop inflation in the first place, have argued that eternal inflation and the multiverse represent a failure of the theory, not a success. If your model predicts everything, it predicts nothing. If every possible set of physical constants is realized somewhere in the multiverse, then you cannot use the theory to predict what you will measure, and a theory that cannot be tested is not by the traditional standard, a scientific theory at all. Steinhardt has spent the last 2 decades developing alternative cosmological models, including cyclic models, where the universe goes through repeated phases of expansion and contraction, specifically to avoid the multiverse conclusion. And both sides have a point. That is what makes it so hard. So where does this leave us with the real size of the universe? In a genuinely strange place. The observable universe, 93 billion light-years across, is the largest thing we can study directly. The full universe, if general relativity and inflation are correct, is vastly larger, possibly infinite. And if eternal inflation is correct, our entire universe, observable and unobservable alike, may be one bubble in a structure so large that the word large stops functioning. Not infinite in the way that a number line is infinite, stretching in one direction forever, but infinite in a more layered sense, with new regions constantly being created, each one potentially as large as our own cosmos, embedded in a space that is itself expanding without limit. And you are lying here, in a room, on a planet orbiting a middle-aged star in one arm of a fairly typical spiral galaxy, inside an observable universe that is itself a speck. And the light from the cosmic microwave background is passing through the walls right now, the same ancient glow that carries the evidence for all of this, arriving from every direction, from a surface that was once close enough to touch and is now 46 billion light-years away. But the size of the universe, as staggering as it is only half of the story that the cosmic microwave background has to tell. Because that ancient light does not just tell us how big things are, it tells us how old things are, and how everything we see today grew from almost nothing, and the way it tells us involves a kind of music that was playing before there were any stars to hear it. The fluctuations in that background, the tiny variations in temperature from one patch of sky to another, are not random noise. They are the frozen imprint of sound waves that once rippled through the entire visible universe, and the pattern they left behind turns out to be one of the most precise measuring tools in all of science. Let's stay with it for a while, because what happened inside the early universe is genuinely one of the strangest and most beautiful things physics has ever uncovered, and it connects directly to the question of how big everything really is. So picture the universe about 380,000 years after the Big Bang. That sounds like a long time, but cosmically, it is barely a breath. Before that moment, the universe was so hot and so dense that atoms could not hold together. Electrons moved too fast to settle into orbit around a nucleus. Every photon, every particle of light was constantly colliding with free electrons, scattering in random directions, unable to travel any meaningful distance before being knocked off course. The universe was opaque, like fog, like the inside of a star. Light existed everywhere, but it could not go anywhere. And in that dense, opaque plasma, something was happening. Gravity was pulling matter inward toward regions that were very slightly denser than their surroundings. Just slightly. The differences were tiny, on the order of 1 part in 100,000. But gravity does not need much of a head start. It pulls matter inward, and as matter falls inward, it compresses, and compression heats the gas, and the heat creates pressure, and the pressure pushes back outward. And then the pressure wins for a moment. The gas expands, cools, loses pressure, and gravity pulls it back in again. In and out. Compress and expand, over and over. That is a sound wave, not metaphorically, literally. A sound wave is a pressure oscillation moving through a medium, and the early universe was a medium, a hot, dense plasma filling all of space, and pressure waves were rippling through it at a calculable speed, roughly 57% of the speed of light. These waves had been running since the very earliest moments, driven by the initial density variations that inflation had stretched from quantum fluctuations into macroscopic seeds. And they kept running, oscillating back and forth for the entire 380,000 years that the universe remained opaque. Then, quite suddenly on a cosmic timescale, the universe cooled enough for electrons to combine with nuclei and form neutral atoms. Hydrogen, mostly. And neutral atoms do not scatter photons the way free electrons do. The fog cleared. Light was released, free to travel in straight lines for the first time, and it has been traveling ever since. That light is the cosmic microwave background, and the pattern frozen into it, the map of slightly hotter and slightly cooler patches across the sky, is a snapshot of those sound waves at the exact moment they stopped. The music froze. Here's the thing about sound waves. They have harmonics. If you have a wave that has been oscillating in a cavity, or in this case across the entire universe, for a known amount of time, and you know the speed of sound in the medium, you can calculate the wavelength of the fundamental mode and all of its overtones. The fundamental mode is the wave that has had time to complete exactly 1/2 oscillation, compressing once, by the time the universe became transparent. The first overtone completed a full oscillation, compressing and then expanding. The second overtone completed 1.5 oscillations, and so on. Each of these modes leaves a characteristic imprint on the pattern of temperature variations. When cosmologists measure the cosmic microwave background and break its pattern down by angular scale, asking how much variation there is on patches of sky that are 1 degree across versus 1/2 degree versus 1/4 degree, they find a series of peaks. The first peak, the strongest, corresponds to the fundamental mode. The second peak corresponds to the first overtone. The third peak to the second overtone. And the relative heights and positions of those peaks encode an extraordinary amount of information about the universe. The position of the first peak, for instance, tells you the geometry of space. Think about why. You know how big the sound wave was at the moment the universe became transparent, because you know the speed of sound and you know how long the wave had been running. That gives you a physical size, a known length, imprinted on a surface that is now 46 billion light-years away, and you can measure the angle that length subtends on the sky. If space is flat, that angle comes out to about 1 degree. If space is positively curved, like the surface of a sphere, the angle would be larger, because curved space acts like a magnifying lens. If space is negatively curved, the angle would be smaller. The measurement, refined over decades by Kobe, then by the boomerang balloon experiment in the late 1990s, then by WMAP launched in 2001, and finally by the Planck satellite launched in 2009, is extraordinarily clear. The first peak sits at almost exactly 1 degree. Space is flat, or so close to flat, that any curvature is below the precision of our instruments. Planck's final results, published in 2018, constrained the curvature parameter to within 0.5% of 0. Flat. Now, you might be thinking, what does flat space have to do with the size of the universe? Everything, as it turns out. Because the geometry of space determines whether the universe is finite or infinite, and the answer is more subtle than you might expect. If space were positively curved, like the surface of a sphere, the universe could be finite and yet have no edge. You could travel in a straight line and eventually come back to where you started, the same way you can walk in a straight line on the surface of the Earth and circumnavigate it. A positively curved universe would be large, possibly enormously large, but it would contain a finite amount of space, a finite number of galaxies, a finite volume. But flat space, Euclidean space, the kind of space where parallel lines stay parallel forever, and triangles have angles that add up to exactly 180 degrees. That kind of space can extend without limit. It does not have to. There are some exotic topologies where flat space can still be finite, like a torus, where space wraps around on itself without being curved. Cosmologists have looked for evidence of that kind of wrapping, searching for repeating patterns in the cosmic microwave background that would indicate the universe is a hall of mirrors, and they have not found any. The simplest interpretation of a flat universe, and the one that inflation predicts, is that it goes on forever. Let's sit with that for a second. The observable universe, the sphere of space from which light has had time to reach us, is 93 billion light-years across. That is already a number that resists intuition. But if space is flat and extends without limit, then the observable universe is not a small fraction of the whole. It is an infinitely small fraction, not like a golf ball inside a warehouse, more like a golf ball inside something that has no walls, no ceiling, no floor, and no edge, something for which the word inside barely applies. And this is where the question we have been circling all evening, the question of how big the universe really is, starts to become genuinely difficult. Because the word size assumes you can put a number on it. 93 billion light-years is a size. A trillion light-years would be a size. But infinity is not a size. It is the statement that no size exists, that no matter how far you go, there is more. And the measurements, the actual hard-won data from Planck and from every other instrument that has studied the geometry of space, are consistent with that. They do not prove the universe is infinite. They prove that if it is finite, it is so large that its curvature is undetectable, which means it is at minimum hundreds of times larger than the observable universe, and possibly, probably, without end. And here is where the title of this whole conversation earns itself, because in a certain sense, the real size of the universe is worse than infinite. Not because the universe is larger than infinity. That is not a coherent idea, but because the kind of infinity involved is more disorienting than the simple kind. Think about what an infinite flat universe actually means in physical terms. If the universe is infinite and roughly uniform, which the cosmic microwave background suggests it is on large scales, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if the laws of physics are the same everywhere, which every observation supports, then the possible arrangements of matter in any given region are finite, because there are only so many ways to arrange a finite number of particles in a finite volume. The number is huge, incomprehensibly huge, but it is finite. An infinite universe with a finite number of possible configurations means that configurations must repeat. Somewhere, impossibly far away, far beyond the observable universe, far beyond any distance that light will ever cross in any amount of time, there is a region of space where the particles happen to be arranged in exactly the same way they are arranged here. Not similar, identical. This is not mysticism or speculation. It is a straightforward consequence of the mathematics pointed out by Max Tegmark, among others, and it follows from two premises that are both supported by observation: that space is infinite and that physics is uniform. The distance to such a repeat is calculable in principle. Tegmark estimated it at roughly 10 to the power of 10 to the power of 29 meters, a number so large that writing it out would take more digits than there are particles in the observable universe. It is not a distance anyone will ever cross or a region anyone will ever observe. But if the premises hold, it is there. And so is every other possible arrangement of matter, somewhere, including arrangements that differ from this one by a single atom, or by a single photon, or by nothing at all. This is what I mean when I say the real size is worse than infinite. Infinite is a word we can almost get comfortable with. It means keeps going. But an infinite universe that is also uniform means that every possible version of every possible region exists, not as a hypothetical, not as a quantum branching, but as a physical place, separated from us by distances that make the observable universe look like a single point, and we will never see any of it. Not because our telescopes are not good enough, but because the expansion of space ensures that light from those regions will never arrive. So the cosmic microwave background, this ancient light that is passing through your room right now, does two things at once. It tells us the geometry of the universe with extraordinary precision, confirming that space is flat. And by confirming that space is flat, it opens the door to an infinity that is far stranger and far larger than the word usually implies. The sound waves that rang through the early universe, the pressure oscillations of hot plasma driven by gravity and radiation, froze into a pattern that we can decode, and the message in that pattern is that there is no edge, no boundary, no wall at the end. But geometry is only one of the things encoded in those peaks. The relative heights of the first and second and third acoustic peaks carry something else, something that connects directly to what the universe is made of, and how much of it is made of something we have never directly detected and do not yet understand. Because the way those sound waves behaved, the way gravity and pressure competed in the early universe, depended on how much matter there was and what kind of matter it was. And the answer to that question turned out to be deeply, profoundly strange. Because the peaks told us that the ordinary matter we know, the protons and neutrons and electrons that make up everything you have ever touched, everything you can see, every star and planet and grain of dust, accounts for only about 5% of the total energy content of the universe. 5%. And roughly 27% is something else entirely. Something that has mass, something that pulls gravitationally, something that shaped the way those sound waves rang through the early plasma, but something that does not interact with light. It does not glow. It does not absorb. It does not scatter. It does not reflect. It is, in every optical sense, invisible. And we call it dark matter, which is one of those names that sounds like it explains more than it actually does. Here's the thing about dark matter. The name makes it sound like it is ordinary matter that happens to be dark, like a rock floating in space that nobody has shown a flashlight on yet. But that is not what dark matter is. Dark matter is dark because it does not participate in electromagnetism at all. Light is an electromagnetic wave, and dark matter is transparent to it in both directions. Photons pass through dark matter the way neutrinos pass through your hand. There is no interaction, no coupling. The reason you can see the chair across the room, or the wall, or your own fingers, is that the atoms in those objects have electrons, and electrons interact with photons, and that interaction is what seeing is. Dark matter does not do that. Whatever it is made of, it lacks the property that makes things visible. So calling it dark is a little like calling a ghost quiet. It is not that the ghost chose not to speak. It is that the ghost has no mouth. And yet we know it is there. We know it with the same confidence that we know the Earth orbits the Sun. Not because we have captured a particle of it in a jar, but because its gravitational effects show up everywhere we look, in so many independent ways, measured by so many independent methods, that the alternative, that gravity itself works differently than we think, has been tested and mostly fails to account for the full picture. So how did we get here? The story usually starts with Fritz Zwicky, and that is fair, because Zwicky was the first person to notice the problem clearly enough to put a number on it. In 1933, Zwicky was studying the Coma Cluster, a dense collection of over 1,000 galaxies about 320 million light-years away. He measured the velocities of the galaxies in the cluster by looking at their redshifts, the way their light was stretched by their motion, and he found that they were moving far too fast. The galaxies at the edges of the cluster were whipping around at speeds that should have flung them out into empty space long ago. The visible mass of the cluster, all the stars and gas you could see, was nowhere near enough to generate the gravitational pull needed to hold those galaxies together. Zwicky calculated that the cluster needed about 400 times more mass than was visible. 400 times. He called the missing stuff dunkle materie, dark matter, and then the field mostly ignored him for about 40 years. Now, you might be thinking that 400 was too high, and you would be right. Zwicky's estimate was off, partly because the distance scale was not well calibrated in 1933, partly because he did not account for all the hot gas between galaxies that we now know emits X-rays. But the direction of his result was correct. There was far more mass than anyone could see. He was right about the problem, even if the magnitude needed adjusting. And the reason the field ignored him was not that his reasoning was bad. It was that nobody knew what to do with the answer. If most of the universe is made of something invisible, what are you supposed to do next? There was no instrument that could detect it, no theory that predicted it, and no framework for thinking about matter that does not interact with light. So astronomers moved on to problems they could solve, and the missing mass sat quietly in the literature, waiting. It waited until the 1970s, when Vera Rubin and Kent Ford started measuring something deceptively simple. They were looking at spiral galaxies, galaxies like our own Milky Way, and they were measuring how fast stars orbit the center at different distances. Think about the solar system for a second. Mercury, close to the Sun, orbits fast. Neptune, far from the Sun, orbits slowly. This makes sense because the Sun contains almost all the mass of the solar system, and the farther you are from that mass, the weaker the gravitational pull, and the slower you need to move to stay in orbit. This is called Keplerian rotation, and it is exactly what Newton's laws predict for a system where most of the mass is concentrated in the center. Rubin and Ford expected to see the same pattern in galaxies. Stars near the center should orbit fast, and stars farther out should orbit progressively slower. And for the inner regions of the galaxies, that is roughly what they found. But as they moved outward, measuring the velocities of stars and gas clouds farther and farther from the galactic center, something unexpected happened. The rotation speed did not drop off. It stayed flat. Stars at the very edge of a galaxy were orbiting just as fast as stars much closer to the center, sometimes faster. And this was not one galaxy. Rubin and Ford measured it in galaxy after galaxy after galaxy, dozens of them, and the pattern was always the same. Flat rotation curves, extending far beyond the visible disk of stars. Think about what that means. If the stars at the edge of a galaxy are moving that fast, they need much more gravitational pull to stay in orbit than the visible matter can provide. Either Newton's law of gravity is wrong at these scales, or there is a lot of mass out there that we cannot see. And the mass cannot be concentrated in the center, because that would produce the Keplerian drop-off. It has to be spread out in a vast, roughly spherical halo that extends well beyond the visible galaxy. A halo of something massive, something gravitationally active, something that does not emit or absorb light. Rubin published these results throughout the late 70s and early 80s, and unlike Zwicky, she had the advantage of timing. By then, theorists had begun to take the idea of non-luminous matter seriously. Jim Peebles at Princeton had been arguing on theoretical grounds that the universe needed more matter than was visible. Jeremiah Ostraker and Peebles had published a paper in 1973 showing that disk galaxies, left to themselves with only their visible mass, are unstable. They would buckle and distort within a few 100 million years. But real galaxies are stable. They have been spinning smoothly for billions of years. The only way to stabilize them in the simulations was to embed the disk in a massive, invisible halo. So when Rubin's observations came along, showing exactly the gravitational signature of those halos, the theoretical framework was ready to receive them. And this is where the cosmic microwave background comes back in. Because the acoustic peaks we talked about, the ones frozen into the pattern of the CMB, provide a completely independent measurement of how much dark matter there is. The way those peaks work is that the height of the first peak relative to the second peak depends on the ratio of ordinary matter to dark matter in the early universe. Ordinary matter, the baryons, feels both gravity and radiation pressure. Dark matter feels only gravity. So in the early plasma, ordinary matter was being pulled into dense regions by gravity and then pushed back out by the pressure of the photons it was coupled to. That is the oscillation, the sound wave. But dark matter was not coupled to the photons. It just fell into the gravitational wells and stayed there, deepening them. The more dark matter there was, relative to ordinary matter, the deeper those wells became, and that changed the relative heights of the peaks in a very specific, calculable way. When the Planck satellite measured those peaks with extraordinary precision in 2013, and then again in its final data release in 2018, the answer was clear. The universe is about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. And here is what makes this so compelling. That ratio, 5 to 27, was derived from the pattern of light that left the universe when it was only 380,000 years old. And it agrees, within the uncertainties, with the ratio you get from galaxy rotation curves measured in the present-day universe, from gravitational lensing of distant galaxies, from the way galaxy clusters merge, from the large-scale distribution of galaxies across billions of light years. These are completely different methods, looking at completely different things, at completely different times in cosmic history, and they all converge on the same number. That is not a coincidence. That is a measurement. So what is it? That is the question that has been driving an entire branch of physics for decades now, and the honest answer is that we do not know. The leading candidates for a long time were a class of hypothetical particles called WIMPs, weakly interacting massive particles. The idea was elegant. If you extend the standard model of particle physics in certain natural ways, you predict the existence of a new particle that has mass, that interacts through gravity and possibly through the weak nuclear force, but that does not interact electromagnetically. And when you calculate how many of these particles would have been produced in the early universe and how many would survive to the present day, you get a density that is remarkably close to the observed dark matter density. This coincidence was so striking that physicists called it the WIMP miracle, and it motivated an enormous experimental effort. Deep underground, in mines and tunnels shielded from cosmic rays, teams built detectors designed to catch the rare occasion when a WIMP might bump into an ordinary atom. The Xenon experiment in Italy, LUX and then LZ in South Dakota, Pandax in China, all of them using tanks of ultra-pure liquid xenon, cooled to -100 degrees, watched by arrays of photomultiplier tubes waiting for a single flash of light from a single collision. These are some of the most sensitive instruments ever built. They can detect the energy deposited by a single atom recoiling from a collision with something invisible, and they have found nothing. Year after year, the sensitivity improves, the exclusion limits tighten, and the WIMPs do not appear. That does not mean WIMPs do not exist. It means that if they do exist, they interact even more weakly than the simplest models predicted, which makes the WIMP miracle feel less miraculous and more like a coincidence. Other candidates have moved into the conversation. Axions, originally proposed to solve a different problem in particle physics, are now a serious dark matter candidate, and experiments like ADMX are searching for them using resonant microwave cavities tuned to convert axions into detectable photons. Sterile neutrinos, primordial black holes, superfluid dark matter, each proposal has its own signature, its own detection strategy, its own set of problems. And then there is the other possibility, the one that never quite goes away. Maybe there is no dark matter. Maybe gravity itself behaves differently at very low accelerations than Newton and Einstein predicted. Mordechai Milgram proposed this idea in 1983, calling it modified Newtonian dynamics, or MOND, and it does something remarkable. With a single new parameter, a characteristic acceleration scale, it reproduces the flat rotation curves of galaxies without any invisible matter at all. For individual galaxies, MOND works surprisingly well, but it struggles with galaxy clusters, where it still needs some unseen mass, and it has never been fully reconciled with general relativity in a way that reproduces the CMB acoustic peaks as naturally as the dark matter model does. The tension between MOND and the standard cosmological model is real and ongoing, and it is one of those places where the evidence has not yet spoken clearly enough to close the door. But here is what matters for the size of the universe, for the question we have been circling all evening. The amount of dark matter determines how structure formed. It determines how fast galaxies assembled, how they clustered, how the cosmic web of filaments and voids took shape over billions of years. And the cosmic web, this vast network of matter stretching across the observable universe, is itself a kind of ruler. Because the same baryon acoustic oscillations that left their imprint in the CMB also left their imprint in the distribution of galaxies. That frozen sound wave, that preferred separation of about 490 million light-years in today's expanded universe, shows up as a slight excess in the probability of finding two galaxies at that specific distance apart. And measuring that distance at different epochs, at different redshifts, gives you a way to track how the universe has expanded over time. It is called the BAO standard ruler, and it is one of the most powerful tools in cosmology. But to use it, you need to know the dark matter density, because dark matter shaped the growth of those structures. Which brings us to a problem that has been quietly building for the last several years: a discrepancy between two ways of measuring how fast the universe is expanding right now. Because the Hubble constant, that number Edwin Hubble first estimated and that generations of astronomers have been refining ever since, turns out to give a different answer depending on how you measure it. And the difference is not small enough to ignore. It is not large enough to be obvious. It sits right in the uncomfortable middle, where it might be a clue to something genuinely new about the universe, or it might be a systematic error that somebody has not found yet. And the story of that tension, the so-called Hubble tension, is one of the most consequential open questions in all of cosmology, because it touches directly on whether our model of the universe's size and expansion history is actually complete, or whether there is a piece missing that we have not identified yet. So let's talk about what this tension actually looks like, because the numbers matter here, and they are surprisingly specific. On one side, you have the cosmic microwave background. The Planck satellite, which we talked about earlier, measured the tiny temperature fluctuations in that ancient light with extraordinary precision, and from those measurements, combined with the standard model of cosmology, you can extract a value for the Hubble constant. That value comes out to about 67.4 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So what that number means is that for every megaparsec of distance between you and a galaxy, that galaxy is receding from you at an additional 67.4 kilometers per second. And the uncertainty on that measurement is small. Planck's error bars are less than 1%. It is an astonishingly tight number. On the other side, you have the local measurement. This is the one that comes from building a distance ladder, the method we talked about much earlier, where you start with nearby stars whose distances you can measure directly using parallax. Then you use Cepheid variable stars to reach farther out, and then you use type 1a supernovae to push all the way into the smooth expansion of the universe. The team that has pushed this method the hardest is led by Adam Rees, the same Adam Rees who shared the Nobel Prize for discovering the accelerating expansion back in 1998. His group, called SH0ES, has spent more than a decade refining every rung of that distance ladder, checking for systematic errors, recalibrating the Cepheid measurements using Hubble Space Telescope observations, cross-referencing with different galaxy samples. And their answer, as of their most recent major publication, is about 73.0 kilometers per second per megaparsec. The uncertainty on that number is also small, around 1.4%. Now here's the thing: 67.4 versus 73. That is a difference of about 8%. And in everyday life, 8% does not sound like much. If someone told you a city was 8% farther away than you thought, you would shrug. But in precision cosmology, where both teams are claiming uncertainties of around 1%, those two numbers are separated by about 5 standard deviations, 5 sigma. And in statistics, 5 sigma is the threshold that physicists traditionally use to declare a discovery. It is the point where you say this is almost certainly not a coincidence, not a fluke, not a random fluctuation. The probability of getting a 5 sigma discrepancy by chance alone is about 1 in 3.5 million. So either somebody is making a mistake they have not found yet, or the universe is telling us something. Let's take the first possibility seriously, because that is what good science demands. Systematic errors are subtle, and they are everywhere. The distance ladder is a chain, and every chain is only as strong as its weakest link. if the Cepheid calibration is slightly off, if there is some unrecognized population effect in the Type 1a supernovae, if the parallax measurements from the Gaia satellite have a tiny bias at the distances where they anchor the Cepheids, then the whole ladder shifts. Rees and his team have spent years hunting for exactly these kinds of problems, and they have not found one large enough to close the gap. But that does not mean one does not exist. It means they have not found it yet. On the Planck side, the situation is different, but equally worth scrutinizing. The CMB measurement does not give you the Hubble constant directly. What it gives you is a snapshot of the universe at an age of about 380,000 years, and then you use the standard cosmological model, the one called lambda CDM, to evolve that snapshot forward 13.4 billion years to the present. The Hubble constant you get out is only as good as the model you put in. If lambda CDM is missing a component, if dark energy behaves differently than a cosmological constant, if there is an extra species of neutrino or some other form of radiation we have not accounted for, then the number you extract from the CMB could be wrong. Not because the CMB data is wrong, but because the bridge you built from then to now has a flaw in it. And this is where the tension gets genuinely interesting, because it is not just two teams disagreeing. It is two entirely different methods, measuring the universe at two entirely different epochs and getting answers that do not match. The CMB method looks at the infant universe and projects forward. The distance ladder method looks at the nearby universe and measures directly. They should agree. For decades, the uncertainties were large enough that they did agree within the errors. But as both methods got more precise, the errors shrank, and instead of converging on the same number, they pulled apart. Think about what that means for a second. If the discrepancy is real, if it is not a systematic error on either side, then something about the expansion history of the universe is different from what lambda CDM predicts. Something happened between the era of the CMB and now that the model does not account for. And that something would change our understanding of how big the observable universe actually is, because the size of the observable universe depends on the entire expansion history, every phase of it, from inflation, through radiation domination, through matter domination, through the current dark energy-dominated era. If any of those phases behaved differently than we think, the total distance that light has been able to travel, and therefore the size of the sphere we can see, changes. Several ideas have been proposed. One of the more discussed ones is called early dark energy. The idea is that there was a brief period, shortly before recombination, when an additional component of dark energy was active, something that boosted the expansion rate for a short time and then faded away. If that happened, it would change the sound horizon, the physical size of those baryon acoustic oscillations at the time of the CMB. And that would shift the Hubble constant you extract from the Planck data upward, closer to the local measurement. It is a clever idea, and some versions of it can reduce the tension. But it comes at a cost. It tends to worsen the fit to other aspects of the CMB data, particularly the way structures grew over time. You fix one thing and you break another. As of now, no early dark energy model has convincingly resolved the tension without introducing new problems. Another approach involves modifying the behavior of neutrinos or adding new particles that act like radiation in the early universe. These would also change the expansion rate before recombination and shift the inferred Hubble constant. But again, the CMB data is so precise that adding new components is tightly constrained. You cannot just throw in extra particles without affecting the damping tail of the power spectrum, the way the CMB fluctuations fade out at small scales, and Planck measured that damping tail beautifully. There is also the possibility that the answer lies not in the early universe, but in the late universe. Maybe dark energy is not constant. Maybe it has been changing over time, getting slightly stronger, or behaving in a way that lambda CDM does not capture. The Dark Energy Spectroscopic Instrument, DESI, which began its main survey in 2021 from a telescope in Arizona, is designed to measure the expansion history with unprecedented precision by mapping tens of millions of galaxies and quasars across a huge volume of space. Its early results, released in 2024, showed hints, tentative but genuinely interesting hints, that dark energy might not be perfectly constant. The equation of state parameter, the number that describes how dark energy's pressure relates to its density, seemed to drift slightly over time in a way that a pure cosmological constant would not allow. The statistical significance was not overwhelming, and the DESI team was careful to say so. But it was enough to make people pay attention, because if dark energy is evolving, it would affect the expansion rate in exactly the regime where the Hubble tension lives. And then there is the possibility that the tension is telling us something we have not even thought of yet. That is always on the table in science, and it is worth remembering. The history of cosmology is full of moments where a stubborn discrepancy turned out to be the first sign of something fundamental. The mismatch between the predicted and observed perihelion precession of Mercury was a nuisance for decades before Einstein showed it was a consequence of general relativity. The missing solar neutrinos were a headache for 30 years before they turned out to be evidence that neutrinos have mass and oscillate between flavors. Sometimes the universe is not wrong, and the measurement is not wrong. The framework is just incomplete. But we should also hold space for the less dramatic possibility, which is that someone, somewhere, has a systematic error they genuinely cannot see yet. In 2023, a team using the James Webb Space Telescope re-observed some of the same Cepheid variable stars that the SH0ES team had calibrated with Hubble, and Webb's sharper infrared vision allowed them to check whether crowding, the blending of light from nearby stars in Hubble's slightly blurrier images, was biasing the Cepheid brightness measurements. The result was that crowding did not seem to be the culprit. The Webb Cepheids gave essentially the same distances as the Hubble Cepheids. That was a significant check because crowding had been one of the most plausible sources of systematic error. But it did not close the case. There are other rungs on the ladder and other possible biases, and the work continues. What makes the Hubble tension so compelling and so relevant to the question we have been circling all evening is that it sits right at the intersection of measurement and model. It asks whether the universe we can see, this sphere 93 billion light-years across, is really the size we think it is, expanding at the rate we think it is, filled with the components we think it is filled with. And the honest answer, right now, is that we are not entirely sure. The model works extraordinarily well across a huge range of observations, but there is this one crack, this one place where two of our best measurements do not agree, and nobody has been able to make it go away. And the reason that matters for the size of the universe is subtle but important. Because the observable universe is not a fixed thing. It is defined by the expansion history. Change the expansion history, even slightly, and you change the co-moving distance to the last scattering surface, the distance to the farthest galaxies we can see, the total volume of space that has ever been in causal contact with us. The 93 billion light-year figure we keep using is a product of lambda CDM with specific parameters. If those parameters shift, the number shifts with them. Not by a huge amount, probably. But the point is that even the size of the observable universe, the thing we can in principle measure, is model dependent. It depends on getting the physics right. And beyond the observable universe, in that vastly larger space that inflation implies, the question of size becomes something else entirely. Because out there, beyond the cosmic horizon, the universe may not just be more of the same. It may be something fundamentally different. Different in ways that make the word size start to lose its grip. Let's stay with that for a moment, because this is where the evening has been heading, really, from the very beginning. We started with distances we could measure, rungs on a ladder, parallax and Cepheids and supernovae. We worked outward through the expansion itself, through the cosmic microwave background and the baryon acoustic oscillations baked into the distribution of galaxies. We watched the observable universe grow from something we could almost hold in our heads, a sphere of light, to something 93 billion light-years across, a number that already strains any honest attempt at comprehension. And now we are at the edge of that sphere, looking outward into territory where measurement cannot follow, and asking what is actually out there. The first thing to say, and it is worth saying plainly, is that nobody knows. That is not a failure of science. It is a boundary condition. The observable universe has a horizon, the farthest distance from which light has had time to reach us since the universe became transparent. And beyond that horizon, information simply has not arrived. It is not that the universe ends there. It is that our ability to see ends there. The universe keeps going. The question is how far and in what form, and whether how far is even the right question anymore. Now, if inflation is correct, and the evidence we talked about earlier, the flatness, the uniformity of the CMB, the specific pattern of temperature fluctuations, all point strongly towards some version of inflation being correct, then the universe beyond our horizon is not just a little bigger than what we can see. It is almost absurdly bigger. The numbers people throw around vary depending on the model, but one estimate that comes up in the literature, from a paper by the physicist André Linde, suggests that during the inflationary epoch, the universe expanded by a factor of at least 10 to the power of 26. That is the minimum. Some models give 10 to the power of 1,000 or 10 to the power of 1,000,000. And those are not typos. Those are the kinds of numbers that emerge naturally from the equations when you take inflationary expansion seriously. The observable universe, that 93 billion light-year sphere, would be like a single atom compared to the volume of the Earth, or smaller, depending on the model, much smaller. The analogy breaks down because there is no familiar comparison that captures a ratio of 10 to the power of 1,000,000 to 1. You just have to sit with it and let it be what it is. And here is where the word infinite starts to feel, strangely, almost too small. Because if the universe is spatially flat, which the CMB data tell us it is to extraordinary precision, and if inflation lasted long enough, which even conservative models suggest it did, then the universe may be genuinely infinite in extent, not approaching infinity, not very large. Actually, infinite, in the way that the number line is infinite, going on without boundary or edge in every direction, filled with matter and energy and structure as far as you care to go. And the thing about an infinite universe is that it does not have a size. Size is a property of finite things. An infinite universe is not a very big room. It is something categorically different from a room. You cannot stand at its center because every point is equally far from a boundary that does not exist. You cannot talk about its total volume because volume is a number and infinity is not a number. It is the statement that no number is large enough. Think about what that means for the question in the title of this evening. The real size of the universe. If the universe is infinite, then the question does not have an answer in the way you might expect. It is not that we have not measured it yet. It is that the measurement does not exist. The universe is not a thing with a size. It is a thing that contains all possible sizes within it. But it gets stranger than that. And this is the part that is genuinely hard to hold in your head. So let's take it slowly. If the universe is infinite and roughly uniform, which is what the cosmological principle suggests and what the CMB supports, then every possible arrangement of matter that could exist in a region the size of our observable universe does exist, somewhere, given enough space. This is not mysticism. It is combinatorics. There are a finite number of ways to arrange a finite number of particles in a finite volume at a given temperature. The number is enormous, but it is finite. And if you have an infinite volume to work with, every arrangement is realized. Not once. An infinite number of times. This is the argument that Max Tegmark, the MIT cosmologist, laid out carefully in his work on the multiverse, and it follows from nothing more exotic than the assumption that space is infinite and statistically uniform. You do not need extra dimensions. You do not need string theory. You just need enough room. The implication is that somewhere, impossibly far away, far beyond any horizon we could ever reach even in principle, there is a region of space where the particles happen to be arranged in exactly the same configuration as they are here. The same galaxies, the same stars, the same planets, the same you lying in the same position, listening to the same words. Not a copy in some metaphysical sense, just another patch of the same universe where the dice, rolled enough times, came up the same way. The nearest such duplicate, Tegmark estimated, would be roughly 10 to the power of 10 to the power of 29 meters away. That number is so large that writing it out in full, digit by digit, would require more paper than exists in the observable universe. It is not a distance you could ever cross. It is not a distance that light could ever cross, even given infinite time in an accelerating universe. It is a distance that exists only as a mathematical consequence of infinity and uniformity. Now, you might be thinking, does this actually matter? Is this physics or is it philosophy dressed up in equations? And that is a completely fair question, one that working cosmologists argue about. The honest answer is that it sits right on the boundary. The infinite universe is not something we can test directly because we cannot see beyond our horizon. But it is not pure speculation either, because it follows from models that are tested, inflation and general relativity, and the measured flatness of space. It is a prediction of our best physics that we cannot verify with our best instruments, and that is an uncomfortable place for science to be. But it is where the evidence has led. What we can say, with real confidence, is that the observable universe is not the whole story. Even the most conservative reading of the data tells us that. The CMB tells us space is flat to within 0.5%. A flat universe that is finite would need some kind of topology, some way of wrapping around on itself, like the surface of a torus, and searches for that kind of signature in the CMB, repeating patterns that would show up if space looped back, have found nothing. The simplest interpretation of a spatially flat universe with no topological signal is that it just keeps going. And then there is the question of eternal inflation, which we touched on earlier. Alan Gough's original inflationary model, and the versions refined by Linda and by Paul Steinhardt and Andreas Albrecht all share a feature that was not immediately obvious when they were first proposed. In most versions of inflation, the field that drives the expansion does not stop everywhere at once. It stops in patches. Our observable universe is one such patch, a region where inflation ended and the energy converted into matter and radiation and all the structure we see today. But between the patches, inflation continues. And in those still inflating regions, new patches are constantly forming, each one a universe in its own right, each one potentially with different physical constants, different particle masses, different forces. This is the eternal inflation picture, and it is not a fringe idea. It emerges naturally from the same equations that solve the horizon and flatness problems. Linda has called it the most likely consequence of inflationary theory, not an optional add-on, but something you have to work hard to avoid. In this picture, the universe is not just infinite in the way a flat plane is infinite. It is generative. It is producing new regions of space continuously, each one expanding, each one cooling, each one developing its own structure or failing to. The total ensemble is not just larger than what we can see. It is larger than any single framework can describe, because the frameworks themselves, the physical laws, may vary from patch to patch. So when we ask about the real size of the universe, we are asking a question that has at least 3 different answers depending on what we mean. There is the observable universe, 93 billion light-years across, model-dependent, measurable in principle, and the thing that all of our astronomy actually describes. There is the universe beyond the horizon, the continuation of our own inflationary patch, which may be infinite, and which contains, if it is, every possible arrangement of matter, repeated without end. And there is the multiverse, the collection of all patches, which is not a place you could travel to, but a consequence of the physics that best explains what we can see. And none of these answers is really a size. The first is a horizon, not a boundary. The second may be infinite, which is not a size but the absence of one. The third is not even a single space, but a collection of spaces that may not share the same geometry or the same laws. The title of this evening promised something worse than infinite, and maybe this is what that means. Not that the universe is very, very big, but that the question of how big it is does not resolve into a number. It dissolves into a series of deeper questions about what space is, what infinity means physically, and whether our patch of reality is typical or extraordinary. And that last question, whether our patch is typical, turns out to be one of the most important unsettled problems in all of cosmology. Because if eternal inflation is right, and if different patches have different physical constants, then there is a question that no one has been able to answer satisfactorily, a question that sounds simple but has resisted every attempt at a clean solution. It is called the measure problem, and it asks something that you would think would be straightforward. In an infinite collection of outcomes, how do you count them? That is the measure problem. And the reason it matters, the reason it has kept some of the sharpest people in theoretical physics arguing for decades, is that the usual tools of probability simply stop working when the set you are drawing from is infinite. Think about it this way. Suppose you have a bag with 10 marbles, 7 blue, and 3 red. You reach in, you pull one out, and the probability of getting blue is 7 in 10. Easy. Now suppose the bag is infinite. It contains infinitely many blue marbles and infinitely many red ones. What is the probability of drawing blue? You cannot say 7 in 10 anymore because you do not have finite counts to divide. Infinity divided by infinity is not a number. It is undefined. And that is not a technicality. It is a wall. If you cannot assign probabilities, you cannot say what is likely, what is unlikely, what counts as a prediction, or what counts as a surprise. And science, at its core, runs on the ability to say that a measurement was expected or unexpected given a theory. Without that, you do not have a theory at all. You have a story. This is exactly the situation that eternal inflation creates. If the inflationary multiverse is real, then every possible combination of physical constants is realized somewhere, in some patch, and each combination is realized infinitely many times. So when you ask why our patch has the particular values it does, the particular strength of gravity, the particular mass of the electron, the particular density of dark energy, the answer, because those values occur in some patches, is trivially true. It is also trivially true of every other set of values. Nothing is special, nothing is surprising, and therefore, nothing is explained. The theory predicts everything, which is the same as predicting nothing. Alexander Vilenkin, one of the physicists who helped develop eternal inflation in the first place, has spent years working on this. So has André Linde. So has Alan Guth. They are not fringe figures circling the problem from outside. They are the architects of the framework, and they are the first to tell you that the measure problem is not solved. Various proposals exist. You can try to regulate the infinity by starting from a single point and expanding outward, counting only the events that happen before some cutoff, and then taking the limit as the cutoff goes to infinity. This is called a geometric cutoff, and different choices of cutoff give different answers. Vilenkin and his collaborators explored what they called the tunneling measure. Linde and others developed a volume-weighted approach. Raphael Bauso, working from ideas in string theory and black hole physics, proposed the causal diamond measure, which counts only events within the causal past and future of a single observer. Each of these prescriptions gives a different set of probabilities. Each one makes different predictions about what a typical observer should expect to see, and there is no agreed-upon way to choose between them. Here is the part that is genuinely hard to hold in your head. The measure problem is not a gap in the data. It is not waiting for a better telescope or a more sensitive detector. It is a conceptual problem, a problem about what probability means in a physically infinite context, and it may require a shift in the foundations of how we think about prediction itself. Some physicists, like Paul Steinhardt, who helped develop inflation in the early 1980s, have argued that this is grounds for abandoning eternal inflation altogether, or at least for being deeply skeptical of any claim that rests on it. His view, roughly, is that a theory that cannot make predictions is not a theory, and that the multiverse, as currently formulated, falls into that category. Others, like Leonard Susskind, have argued that the multiverse is the price we pay for taking our best theories seriously, and that the measure problem is hard, but not necessarily fatal. The debate is real, it is ongoing, and it is not close to being settled. And so you arrive at a strange place. The question that started this evening, how big is the universe really, has led you through a chain of measurements and ideas, each one pushing the answer further out. The cosmic distance ladder gave you the observable universe. The expansion of space told you that the observable universe is larger than the light travel time alone would suggest. The flatness of space, confirmed by the cosmic microwave background, told you that the universe extends far beyond the horizon, possibly without limit. Inflation told you that the mechanism that made space flat also made it enormous, potentially infinite, And eternal inflation told you that our entire infinite patch might be just one of infinitely many, each with its own properties, its own history, its own version of the question. But the tools we have for making sense of that last layer, for turning it from a picture into a prediction, are not yet adequate. The measure problem sits right at the junction between physics and philosophy, between what we can calculate and what we can meaningfully say. And the honest answer, the one that the people who work on this will give you if you ask, is that we do not know how to handle it yet. We do not know whether the multiverse is a real physical thing or an artifact of pushing a good theory past its domain of validity. We do not know whether the measure problem has a solution that will make the multiverse predictive, or whether it is a sign that the framework needs to be replaced with something we have not thought of yet. What we do know, and this is worth sitting with for a moment, is that none of this uncertainty touches the things we have actually measured. The cosmic microwave background is real. Its temperature, 2.725 Kelvin, is one of the most precisely measured quantities in all of science. The baryon acoustic oscillations are real, imprinted in the distribution of galaxies exactly where the physics of sound waves in the early universe said they should be. The acceleration of the expansion is real, confirmed by multiple independent methods, Type 1a supernovae, the CMB, baryon acoustic oscillations, all pointing the same way. The flatness of space is real, measured to within a fraction of a percent. The observable universe, 93 billion light-years across, is as solid a number as cosmology has ever produced, even if it shifts slightly depending on which value of the Hubble constant you use. So the uncertainty is not about what we can see. It is about what lies beyond what we can see, and whether the word size even applies there. And maybe that is the honest place to leave it. Not with a number, but with a map that has a well-drawn center and edges that fade into questions. Now, you might be thinking, does any of this matter? If we can never see beyond the horizon, if we can never visit another patch, if the multiverse may or may not be real and we may never know, then why spend an evening on it? And that is a fair question. But here is the thing. The reason these ideas exist is not because someone sat down and decided to speculate about infinity for fun. They exist because the physics that explains what we can see, the physics that predicts the temperature of the cosmic microwave background to 5 decimal places, the physics that tells us where the baryon acoustic peaks should fall and then finds them exactly there. That same physics, followed honestly to its conclusions, points beyond the horizon. Inflation was not invented to create a multiverse. It was invented to explain why the universe looks the way it does, flat, uniform, with just the right pattern of tiny fluctuations. The multiverse is what falls out of the mathematics when you take inflation seriously and ask what happens in the regions we cannot observe. You can choose to ignore those regions. That is a legitimate philosophical position. But the physics does not stop at the horizon, just because our instruments do. And there is something quietly remarkable about that. You are lying here, in a room, on a planet that orbits an ordinary star in an ordinary spiral galaxy, one of something like 200 billion galaxies in the observable universe alone. The light from the most distant objects you could ever see, even in principle, left its source more than 13 billion years ago, when the universe was dense and hot and opaque, and it has been traveling ever since, stretched by the expansion of space from a blinding glow into a faint microwave whisper that fills every cubic centimeter of the room you are in right now. That radiation is real. It is here. It is passing through you at this moment, and it carries in its pattern the shape of the universe as it was when it first became transparent, 380,000 years after everything began. And beyond that light, beyond the horizon it defines, space almost certainly continues. The same hydrogen, the same helium, the same physics, the same patient process of gravity gathering matter into clouds, and clouds into stars and stars into galaxies. How far it continues, we do not know. Whether it continues forever, we cannot say. Whether there are other regions with different rules, we cannot test. But the part of it that we can see, the part that our instruments have mapped and measured and cross-checked and argued over, that part is coherent. It holds together. The numbers from different methods agree, or when they do not agree, like the Hubble tension, the disagreement itself is precise enough to be meaningful, to point toward something specific that we have not yet understood. The real size of the universe is worse than infinite, not because the universe is scary or hostile or indifferent in some cold way, but because the question itself outgrows every answer you give it. You start with a number, 93 billion light years, and that number is real and solid and worth knowing. But it describes a horizon, not a boundary, and the moment you ask what is beyond the horizon, you are in a different kind of conversation, one where the usual meaning of size starts to stretch and thin and eventually dissolve. The universe may be infinite. It may be one of infinitely many. It may be something for which we do not yet have the right language. And all of that is fine. All of that is just the shape of the question at the edge of what we know. Right now, tonight, the expansion is continuing. Every galaxy beyond our local group is drifting further away, carried by the stretching of space itself, and the rate of that stretching is increasing, gently, steadily, driven by whatever dark energy turns out to be. The cosmic microwave background is still arriving, from every direction, the same faint hum it has been for 13.8 billion years. A little cooler now than it was 1 billion years ago. A little cooler than it will be 1 billion years from now. The atoms in your body were assembled in stars that burned out long before the Earth formed, and the hydrogen in those stars was produced in the first few minutes after the expansion began, when the universe was hot enough to fuse protons and neutrons into nuclei, but cooling too fast to get much further than helium. You are, in a straightforward and literal sense, made of material that has been part of this process from very close to the beginning. Not a visitor to the universe, but a piece of it, briefly arranged into someone who can lie in the dark and wonder how far it all goes. And the answer, the real answer, is that it goes further than we can measure, further than we can model with confidence, and possibly further than the concept of distance can reach. But the part of it that is here, the part that is carrying you through the dark at 600 kilometers per second, relative to the cosmic microwave background, the part that built the carbon in your bones and the oxygen you are breathing, that part is not going anywhere. It has been running for a very long time, and it will keep running tonight, whether or not anyone is still awake to think about it.